All right, guys, we're going to wrap up Chapter 6. All we have to do is talk about the tangent inverse, and then we're going to jump into Chapter 7 and introduce kind of what Chapter 7 is going to target, and then we'll start a little bit of Section 7.1. The tangent inverse, guys, it's the same logic as the sine inverse, cosine inverse, all that kind of stuff. Just giving you a description here. The tangent, obviously, like all the other functions, is periodic. It repeats itself, right? So because of that repetition, we're not going to pass the horizontal line test. Okay? Therefore, it's not going to be one-to-one. So what we need to do is we start restricting the domain. Okay? So maybe we restrict between 2 pi and negative 2 pi. And we look at that and we say, okay, well, that still is an issue because even though there's less places that we fail the horizontal line, there are less multiples of intersections of horizontal lines, we still fail it everywhere, right? So then maybe we say, well, let's look at between negative pi and just pi. It's getting better, isn't it? But do I still fail the vertical line, or sorry, the horizontal line test there? Yeah, pass the vertical, but still fail the horizontal. So that's not what I'm looking for. What do you think I'm going to be looking for here? Yeah, put this over 2. Put that over 2. And now we have our interval for coming up with the inverse. Okay, now part of this graph is actually, obviously they're not drawn in. Okay, and usually asymptotes. So asymptotes, when we draw them in, guys, that's a visual reminder for us, right? Okay. So those are my asymptotes. And then I want you guys to think those are part of your graph. Those are things that when we find the inverse function here, those asymptotes are part of the process. Okay. So when I take some key points that are on the tangent function, like 0, 0. Pi over 4, comma, 1. We had negative pi over 4, comma, negative 1. If we think about it, pi over 6 is going to be square root of 3 over 3. If I go pi over 3, that's going to be the square root of 3. So all those points show up on that tangent, right? What do I need to do with those to show up on the inverse? I need to reflect them. So what's going to happen to the ordered pairs? They flip, right? The x's and y's interchange. The domains and range on inverses interchange. So if I look at point E, like I said, point E was pi over 3, comma, square root of 3. So it's going to be square root of 3, comma, pi over 3. And I get that point right there. And let's just make these blue as I do this. Okay, so that one's blue. So that's on the tangent inverse. If I look at point D, okay, point D was the, what was D? So that's pi over 6. Okay, so ends up being square root of 3 over 3, comma, pi over 6. Okay, so that'll be that point. We had pi over 4, comma, 1, right? Let's make that 1, comma, pi over 4. Get that blue point. 0, 0, obviously. Let's make that blue. And then C is going to be negative 1, comma, pi over 4. Oh, sorry, negative 1, comma, negative pi over 4. Okay. And that's great. That would be a series of points that are going to be on my tangent inverse by flipping the ordered pairs, right? Now think about this thing here. This asymptote if that's at pi over 2, x equals pi over 2, right? If you reflect that, remember, the reason these flipped ordered pairs is because the reflections across this line here, aren't they? Okay? So if I take, and essentially, you can do this by just folding on, take your xy plane and fold on the dotted line. You would see, kind of visualize that in your head, doesn't this portion here of this solid asymptote become kind of that there? That makes sense? Okay? And this solid portion would become kind of visually there, right? So if I ask this thing to take that asymptote, reflect it across there, do you see that happen, right? So when I reflect a curve that has vertical asymptotes across the line y equals x, those vertical asymptotes turn into what kind of asymptotes? Horizontal, okay? And they're a special kind of horizontal asymptote in the fact that we don't cross them, okay? We've talked about how we can cross some horizontal asymptotes algebraically, right? Well, because they were vertical initially, and we knew we couldn't cross those vertical ones, then when we find the inverse, there's no way that we're going to cross the horizontal ones. Does that make sense? Okay. So now, if I were to connect those, those blue, I don't know why I wanted to say orange. If we connect those blue points, okay, do it this way. Choose arctangent of x. That orange curve passes through all of those blue points, right? Okay. So now we're looking at that curve as being the tangent inverse. Is that something we can do? Okay. Now let's look at the tangent inverse. What's your domain for the tangent inverse? What kind of numbers are you allowed to put in for the tangent inverse? All real numbers. You can put in anything that you want. That is different than the cosine and sine, right? The arc sine and the arc cosine, those two functions, the only thing I'm allowed to put in are values between -1 and 1, right? Because when I go opposite over hypotenuse or adjacent over hypotenuse, the hypotenuse is always the largest value, right? Okay. Now here, I'm doing opposite over adjacent, and we don't know whether the opposite side or the adjacent side is going to be the smaller one or the bigger one, right? So that division allows then for ultimately all real numbers to exist. Now, I can plug in anything I want to the arctangent. Okay, so let's say that I plug in, we'll just put A in here, and we'll put a slider here, and I can plug in any number that I want, right? Okay, and remember, the arctangent always gives an angle back, right? That's what all of these functions give back, is an angle, okay? Now, it's in degrees, it won't show me radians with pi in them, so I'm not gonna use that display. But no matter what I put in, do I get a value back? Okay, now I'm only using, obviously, very small values. Let's go -500 to 500, okay? And if I go increments of like 0.001, it's kind of silly, but you can see, let's see here, rounding. Okay, you can see that no matter what I plug in there, it's being evaluating, give me something back, right? Okay, now, eventually, what is that number approaching? Yeah. Okay, it's been like, if I go, let's go out to 5,000. Okay, it's been like 89, like 77.5 as the input value. Okay, so that's, obviously pi is 3, right? Okay, or around 3. So that's all the way out there. Okay, about 25 times further out on the right-hand side of the x-axis, and it's giving me 89.2. But now I get all the way up to these values, all the way up to 1865, and it's still giving me 89 point something, right? Okay, so you see that gap in the input values is huge, but the gap between the two evaluated values is pretty small, right? So what are we seeing this number approaching as x gets larger and larger? 5,000 is at 89.988. I go out to 50,000, if it lets me. I don't know if it'll let me. Okay, so at 5,000, I was at 89.98. Now at 50,000, I'm at 89.998. What is this going to slowly get to? What's that number going to slowly get to? Almost 90, right? Why is that happening? Isn't that thing an asymptote? Isn't 90 pi over 2? Okay. So no matter what I plug in, I'm going to get a value very, 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 very close to 90. Okay. And that's the idea, that the domain is any real number. We're seeing there that I went out to 50,000. I think that's pretty far to show that, yeah, we're probably going to be able to put anything in there we want to. Okay. And I'm getting an output. Okay, so it shows that the domain is all real numbers, and that output, though, is getting closer and closer to that horizontal asymptote. So our range for this thing is negative pi over 2 to pi over 2. Okay, so that's something to make note of that is a little bit different. A little bit different than the sine and cosine. Okay, when I took the tangent inverse, I got a domain of all real numbers. The cosine and sine inverse, those are domains of negative 1 to 1. Okay? Because the tangent inverse has a domain of all real numbers, when we do the tangent of tangent inverse, okay, so we do that composite function, we are always going to get x no matter what is put there. Does that make sense to everybody? Okay? Now, the reason this exists, and we made a kind of a comparison in the last class. If I took, like, f of x, give me a second real quick, this thing's lagging. That's better. All right, so if I take, like, f of x, is equal to, let's go 2x. And g of x is equal to root x. And I asked you to find f composite g of x. You guys remember writing that as f of g of x? Which means that that's f of root x, right? Which now I'm going to take root x and we'll plug it into f, which means it's 2 root x. So that is f of g of x. Okay. Can I evaluate this thing for x being negative 1? If that x right there is negative 1, this x becomes negative 1, and what does that amount turn into? I, which on our real numbers is undefined, right? Okay. So we get an undefined value. Can I take an undefined value and multiply by 2? No, I can't take an undefined value and run it through a second function. So I can only evaluate, if you remember doing this, I can only evaluate f of g of x for the values of g of x in which x is defined. Okay? So I can only evaluate f of g of x there for values of x being greater than or equal to 0. Same thing's happening here with the tangent inverse and tangent functions. I can only evaluate this outer function tangent when this number here, when this function here produces an output. Well, what happens is that we just looked at, no matter what I plug in for x, the arctangent is going to produce an output, right? I'm always going to get something back here. So then if I take the tangent of that thing I got back, I will always get x, for all real numbers. That's contrary to what we talked about with the sine and cosine. The cosine, okay, if I plug in like a 3 right here, cosine inverse of 3, what that means, cosine inverse of 3, we're asking ourselves what angle on the unit circle will spit back an x value of 3. And we know there isn't one, right? It does not exist. That is not a defined value. So we don't know what to put there. We can't put anything there, right? So how can I then take the cosine of nothing? You can't, right? Or I don't want to say nothing because we think of 0. I want to say, how do I take the cosine of the absence of something, right? Okay, it does not exist. You cannot do it. So that's why we have to have that statement for -1 less than or equal to x less than or equal to 1. Because that's the only set of values that are allowed to be plugged into this thing. That's the domain of the innermost function. That's what we talked about in algebra. Okay? All real numbers is the domain of this inner function. Okay? Now, when I take tangent inverse of tangent of x, that is only equal to x for -pi/2 is less than x is less than pi/2. Okay? Because we're going to take the tangent inverse, okay? So when we take the tangent inverse, we have to understand that the function that we're taking the inverse of had to be 1 to 1. Well, the tangent inverse is the inverse of tangent, right? So we make the tangent 1 to 1 by restricting the domain. So I can only plug in -pi/2 to pi/2 because that's the domain we restricted for the tangent, right? Okay? So what this is going to lead us to, guys, and the reason we talk about this, think about what you did in Algebra 1, okay? Probably about the 4th, 5th week of Algebra 1, and you probably even did some of this stuff in like 8th grade, 7th grade math. You were doing a lot of this, like 2x equals 4, 1/2 x equals 3, -3x equals 9. You did little equations like that, right? And the reason you did those little equations is because that then is the last step of every single equation you ever come across, right? Divide by 2 gives me x equals 2. Multiply by 2 gives me x equals 6, right? You did those, okay? Now, why did you do those? You learned those real well because the next thing you did was, okay, 2x plus 1 equals 5. You built upon that equation to something new, right? And now what'd you do? You turn that into 2x equals 4, and you're like, aha, I've done this before. I know what to do now, right? Okay? So you kind of work with backwards almost, with the last step that you're ever going to come towards algebraically, and then you start building on that and see how you, through those built upon equations, how you eventually get back to those ones that you practiced initially. Does that kind of make sense? I don't know the best way to articulate that, but that's hopefully the process that you've recognized or that you've experienced. We're doing the same thing here with learning these inverse functions and doing questions, say, like this one, okay? Because at some point, and you're going to see a little bit of it maybe today and tomorrow, at some point we're going to have an equation that maybe we start off with, let's say that we've got, so we got tangent squared x equals 1. Okay? We square root both sides. And we get tangent of x equals plus or minus root 1, which is just plus or minus 1, right? And now if I'm solving this equation, I don't want to solve for tangent of x. I want to solve for just x, right? So then we ask ourselves, well, how do I get that x to drop out? We inverse both sides, right? And that there, tangent inverse of tangent of x, is this statement right here, correct? Has to give me x, okay? Now, because of this domain here, we're going to be kind of restricted to a certain set of values that we get back. But if I go, so I'm going to take tangent inverse of both sides, so it would give me tangent inverse of 1, which is exactly what this question is getting at, right? So this question is getting at kind of the last step that we're always going to conduct on a trigonometric equation. I want to ask myself, okay, well, what is tangent inverse of 1? What is the angle that I get when I type in tangent inverse of 1 on my calculator? Or what is the angle that is associated with the tangent value of 1 on the unit circle? Or if I go sine divided by cosine on the unit circle, where does that give me a value of 1? What angle measurement? Isn't sine divided by cosine, are they the same thing at pi over 4? Okay, so x here is going to be pi over 4 or 45 degrees. Does that make sense? That's what this is. If I type in tangent inverse on my calculator, now make sure you're in a mode that you are comfortable with. So let me open Dazzle, or not Dazzle, Desmos. Dazzle is what I'm in. Let's see here. If you're comfortable with your radians, okay, you can type in arctangent, get 0.78. That's half of 1.57, which is pi over 2, right? Half of pi over 2 is pi over 4. Or you can change to degrees, which I think most people are a little bit more comfortable. That's a lot nicer number, right? But you see arctangent of 1 is 45, okay? Now, when I do arctangent of -1, now the question is, what do I get back when I do that? Okay, I'm thinking now the sine and cosine still have to be the same amount, right? They both have to be radical 2 over 2, but one is going to be positive, one is going to be negative, correct? Okay, now because we've restricted the domain of the original tangent function, a lot of people are going to say, oh, it's at 3 pi over 4. Okay? But we've restricted the original domain of the tangent to just those two quadrants. Negative pi over 2 to pi over 2, right? So where does the sine divided by cosine end up being opposites in those two quadrants? Say again? Quadrant 4. It's going to be right there, isn't it? Isn't that at negative pi over 4 or negative 45? And that's what you're going to see on any calculator that you type in. You're going to see negative 45. Okay? However, here's what stinks about this. In your equations eventually, they're going to say, write all answers maybe on that interval between 0 and 360, including 0. Okay, well, is negative 45 in there? No. But what is an angle that is coterminal with negative 45? That is inside this interval. 315, isn't it? Okay, think about this. If I take the tangent of negative 45, it gives me negative 1, right? That shouldn't make sense. Aren't these two things inverses? Take tangent negative 45, get negative 1. Plug that into the inverse as the input, get your original output, right? Okay? Or your original value as your output. Well, let's do this with 315. Is it the same information? 315 gives you negative 1. Plug in negative 1. I get 45, which is the same. It's coterminal with 315. Does that make sense? Okay. Those are things to think about, guys, that we have to be paying attention to when we start solving equations. Ultimately, what's going on there is when we're solving these equations, we initially get the negative 45 to be that point right there, right? Where my cursor is. Okay? But what we really want, based on the way the directions are worded, is to come over here and pick up that answer right there. It's the same one, isn't it? It's the same height of negative 1, but it's just now between 0 and 360. If we were to put, let's see here, I don't know if I can do this. The x-axis, yeah, it don't make sense. Let's see here, 2 pi. I don't think I can change it. If I could change this to degrees, my x-axis in degrees, obviously I just put the symbol there. It's not really degrees, right? This spot here would be, right there would be 360 degrees. Right there would be 315. Okay, which is exactly what we were seeing there in degrees. I vaguely remember doing that at one point, being able to transfer my x-axis into degrees. But I think it was a process. So, but that's kind of what we'd be doing with those things. And that so people always say, well, why are we doing this? So they don't initially think about the impact of learning this, and they say, well, I struggle with some of this stuff, so it's going to be gone in a week or so I don't really care. It's not going to be gone in a week or so. Okay, it's going to be even more present in a week or so. Does that make sense, everybody? So my hope is that we're taking this seriously, so that when we get to those last steps of equations, we don't have to explain this again, because it's fundamental. It's a principle that we've learned and that we understand is going to be present, and it's just it will alleviate a lot of stress for you later if you don't have to learn this at the same time you're trying to learn how to solve equations. This one here, okay, when I take tangent inverse of radical 3, remember that radical 3 is a ratio, correct? Okay, so it's a sine divided by a cosine off the unit circle. If I think about like 30 degrees, the tangent of that would be the sine of 30, which is 1/2, divided by the cosine of 30, which is that, right? So that gives me root 3 over 3. So this is the number that is showing up in this this argument here, right? Are those the same? No. Okay? So it's not going to produce, the angle that I produce here is not 30 degrees. However, if I look at this, okay, 60 is sine divided by cosine. Sine of 60 is radical 3 over 2. Cosine is 1/2. If I divide those out, that does give me radical 3, right? So if you're typing in your calculator tangent inverse of root 3, it's going to give you back 60 degrees. Okay? Now, here's what I'm not saying that this is the best approach for you, but something that might help. I know that 30 degrees and 60 degrees for a tangent and multiples of 30 and 60 all the way across the unit circle are always going to produce radical 3 or radical 3 over 3. It's going to produce those two numbers. Okay? Now, I remember that the radical 3 over 3 goes with the 30 because of the 3's. Does that make sense? So that extra 3 in the denominator tells me that the degree is going to be the 30. This starts with a 3. Okay? If I look at the 60, that one doesn't have that extra 3 in it, right? The radical 3, it's only got one 3 in it, so I know that goes with 60. That's the way I kind of associate and pair things up in my mind so that I don't have to do this division every single time I get a problem later on that says tangent inverse of root 3 or tangent inverse of root 3 over 3. Does that make sense? Okay. So root 3 is going to be the one that does not have a 3 in the answer, and then root 3 over 3 will be the one that does have a 3 in the angle. Okay. So 60 degrees or pi over 3 would be what you get there. Okay. Now 20 is probably not a number that you've remembered off the unit circle. Okay, when I divide sine and cosine. Okay, and to be honest with you, all the values on the unit circle that are sine and cosine, none of them were divided out to be 20. Okay, that we know. Okay, there are some on there, but the way you're going to do that is you're simply going to take arctangent or tangent inverse, and you're going to type in 20. And in this case, it gives me 87.13 degrees. Okay? So if I went out to 87.13 degrees on the unit circle, took the y value and the x value and divided them in that order, it's going to equate to 20. Does that make sense? Okay? So that's the tangent inverse. We can talk and discuss what the sine inverse and cosine inverse, what their reciprocal inverse functions look like. For instance, if I'm interested in the arcsecant of x, Wonder if this one will do it. Okay, there's my arc secant. Okay. I'm not going to ask you right now to deal a whole lot with that. We've got the arc cosecant as well. You can kind of see there's a similar relationship, isn't there? Okay. You know, if you put in the secant function, okay, and we restrict that secant function for, I don't know if I can do this on here, 0. Yeah, I don't know. I don't remember the way how to do this for Desmos, how to restrict the domain. But if I were to look at just kind of from here and there, okay, that is going to be then one iteration of the secant function to where we pass the horizontal line test, right? Okay, and then if I reflect that, then I should end up getting that curve. Okay, so the same relationships exist about reflecting across the line y equals x and all that kind of stuff. We're trying to find a domain that is the simplest domain, that is closest to 0, 0, that when we restrict it, we get that function. Okay, do the same thing with secant, and we can do the same thing with cotangent. I think, though, with the stuff that we know, the things that we can do with sine, cosine, and tangent and their reciprocals, it's almost trivial to even deal with the arc sine and arc cosecant, or sorry, arc secant, arc cosecant, arc cotangent. I sent you guys a email that has, so I want to start chapter 7. It has this set of formulas on it, okay? I'm not saying that's all the formulas we're going to cover in this class. There might be more, depending on just our time frame, because there are a lot of formulas in a trigonometric class, okay? My hopes, though, is that if you understand the basics, if you understand sine, cosine, secant, cosecant, all the other reciprocal functions, you understand the quotient functions of tangent equals sine over cosine, we can develop the other ones pretty simply, okay, or pretty easily. The hope, though, is that, you know, I send this in a PDF. I hope you print that off, and it becomes kind of something that you carry with you all the time in doing your homework. Whenever we come to class and we're working on questions in class, I hope you have that in front of you so that we can answer questions a little bit quicker. We can actually be active in answering the questions, because all you got to do is search through that paper and find the answer, because it's really frustrating when I say, okay, guys, what's sine of negative x? And it's silent, and then I have to answer that question because I already know it, right? So I want you guys to be actively involved, because the more you see it, the more you're going to kind of train yourself and embed that information to where you can recall it later, okay? So I just want that additional exposure to this stuff. I will allow portions of this on quizzes and tests, for the mere fact that Rhodes says that's okay. Okay. When I taught trig without Rhodes's governance, I did not use any formula sheets for people. Okay. I actually asked them to remember all these things. Okay. So it is not out of the realm of possibilities that you end up in a course at some point when that's expected. Okay, when you get to a calculus course, some of this stuff is expected for you to know, and it's not going to be provided on test quizzes, that kind of stuff. Okay, I want to talk about a couple of these right off the bat and just kind of dealing with what they are and how we approach them. Obviously, the first thing is, and the reason for the formula sheet, is a lot of these look very similar, right? I would hate for you to be a person that really understands what's going on, but because of the similarity in these things, you do a sign switch or something like that, an SIGN switch, and get everything wrong because of that. Okay, now, my hopes are that eventually you realize that when you get into advanced classes, that the assumption is that you're in those advanced classes because you're an advanced student, and you can do the things that are necessary to retain and learn those informations and not transpose signs and that kind of stuff. But there are a lot of things here that are similar, so keeping them straight is hard. But what these formulas here, these are called addition subtraction formulas. What they basically do is say, okay, if I want to find the sine of 75 degrees, I don't know that off the unit circle, right? Okay, but I know the sine of 30 and I know the sine of 45, don't I? So let's let S be 30, let's let T be 45. That gives me 75. And then I can plug those 30s and 45s into the right-hand side, and that will give me the exact value on the unit circle of the sine of 75 or the cosine of 75. Does that make sense? Okay. What that allows you to do is allow you to take any two numbers in regards to radians or degrees off the unit circle, add them together, and now you can find another angle off the unit circle, or another set of ordered pairs off the unit circle. We have the same thing occurring for things like this, sine of 2x. So let's say I want to find sine of 60. Well, sine of 60 is the same thing as sine of 2 times 30, isn't it? Okay. So could I say 2 sine of 30 cosine 30 multiplied together? That will give me the exact same value as sine of that 60. Okay. They're just relationships that exist all the time that are true. Okay. We've got some what we call formulas for lowering powers. We'll do a little bit with that, not a whole lot though. What we do deal with a lot is half angle formulas. These should show up in calc a lot. Let's say I have a 15-degree angle. I want to find out the sine of a 15-degree angle in the unit circle. Well, what's 15 as a number divided by 2? How can I rewrite 15 so it's a number divided by 2? 30, right? So 15 is the same thing as 30 over 2. So we see u ends up being 30, right? Take 30, place it in the right-hand side of that equation, and now I would know that the square root of 1 minus cosine of 30, which is, what's cosine of 30? Radical 3 over 2. Okay. So I would know that the sine of 15 degrees is equal to positive square root of 1 minus radical 3 over 2 all over 2. Okay. And that's the exact value of the sine of 15 on the unit circle. I can then do that with 45. Okay. I probably wouldn't do it with 60 because isn't that going to give me 30? I already know the sine of 30. Okay. But you can verify that that formula would work with those because you already know the solutions when you do sine of 60 and sine of 30 and that kind of stuff. But those are half angle formulas. And these are over here some of the product formulas. So if I want to add the sine of two angles, we can learn that it is the same as multiplying all this garbage together. Going to find a better way to fit this all on one page, so that's how that worked. We've talked about obviously the reciprocal identities, the quotient identities. We've talked about the Pythagorean identities. Okay, the even odd ones, and that's because of the way the unit circle, or you can think about it, the curves on the XY axes relate to one another in regards to their symmetry. Okay, the sine of negative x is equal to negative sine of x. Cosine negative x is equal to cosine of x, and tangent negative x equals negative tangent of x. A lot of times when you're doing your work, you want your argument to be 1x if we can. It makes things a lot easier. So a lot of the stuff that we do with these formulas is converting maybe sine of negative 2x down to something a little bit simpler. Getting that negative out of there, maybe getting that 2 out of there. So those are procedures that we'll go through. But if I ever see a negative argument, I'm going to attach these even odd properties so that I can make it a positive argument. It makes my work a little bit easier. Okay. The bottom ones we talked about a little bit. They're called cofunctions. Okay. Now, in a cofunction relationship, think about what we did in geometry. In geometry, or even in chapter 5, if I gave you that, let's say this is y, let's say this is x, and this is r, and let's say that I put 40 degrees here. What would be the sine of 40 degrees in this picture? X over R, right? Okay. What would be the cosine of that 50 degrees? Be X over R, wouldn't it? See how those X over R's are the same? So doesn't it mean those two things are the same? If I started with sine of 40, let's say sine of 40, let's say 40 was just theta. How does that equal cosine? How did I get this 50? I took 90 minus that theta, right? Well, in radians, isn't 90 just pi over 2? Okay. So think about this. What do I get? What do I get if I add those? These are angles, right? What do I get if I add an angle of theta plus an angle of pi over 2 minus theta? What do you get when you add those together? Pi over 2 or 90 degrees. What does that meet the definition of? Two angles that add up to 90 degrees are complementary. Where's the co for co-functions come from? The word complementary. Okay? So that's why sine and cosine are the same word, but one has the prefix co in front, right? Because there's a complementary relationship. We call them co-functions. Okay? The co is a complementary concept. Secant and cosecant. Same idea. Tangent and cotangent. Same idea. What is weird, sine and cosine, are they reciprocals of one another? No. Sine is not the reciprocal of cosine and vice versa. They are co-functions, though. Secant and cosecant, are they reciprocals of one another? No. But they are co-functions. Tangent and cotangent, are they reciprocals of one another? Absolutely. And they're also co-functions. Okay, so they're kind of like the oddball out, right? They're the ones that they share both relationships, okay, which the other groupings of two functions do not, okay? If we think about those on the xy axes as curves, we know that they are just translations of one another, left and right, correct? Okay, and to be honest with you, the way they're written up there, they're actually reflections across the y-axis, and then a translation left or right, 90 degrees or pi over 2 radians. But nonetheless, they do have that relationship of being the same all the time. So what's nice about that is if somebody gives me cosine of pi over 2 minus x in my formula, in my equation, I'm not going to deal with that. I'm going to substitute it in sine of x. That's easier to deal with. Okay? So those are all things that we hopefully will eventually start to pay attention to. I just kind of want to run you through real quick. You don't have to write this down. We'll do this one again tomorrow. But I want you to see the purpose of why we're talking about identities. Okay? We're going to see this in an equation at some point. And that's ugly. Okay? So what we want to do is we want to basically say, how can I rewrite this? So would you guys argue that tangent can be rewritten as sine over cosine? That make sense? So I just rewrote that. That's awesome. Okay? Still have that sine of t out here. So this thing here is just that tangent. Now it looks uglier, but now do a little bit of algebra. Isn't that sine squared of t over cosine of t? Does that make sense? Still kind of ugly though. But now I've got two fractions. Can I come up with a common denominator? Does that make sense? And I'll walk through this a little bit more slower tomorrow. But now if I put those under, and I got the same denominator, put them together, add my numerators, what's cosine squared plus sine squared? Isn't it 1? And I got 1 over cosine t. What's 1 over cosine t the same as? Secant t. Those two things I just circled are identical. If I see one of those in the equation, which one would I hope to see in the equation? Secant t. That's easier, right? Now, which one are they probably going to start me with? Cosine t plus tangent t sine t. All right? It's the whole idea, in a question or an equation, if I have like 2x plus 5 times the quantity x minus 3 equals 12, it would be awesome if they would have done that distributive property for me and allowed me just to see all the x's that I currently have, right? But we had to do the evaluation to see really how many x's we have so we can combine them. Same idea here, okay? What is going to happen is, think about this. If you were to put a puzzle together and you put all the pieces face down, are you going to suck at putting that puzzle together? Yeah. It might be something you can do, but it's going to take a long time, right? You flip the pieces over, you can see the colors, you can see the images, you have a better idea how things fit together, right? Okay? That analogy is hopefully going to help you with learning this stuff, because if I were to cosine t plus tangent t sine t, that's a puzzle that I have to put together, okay? If I didn't know the pieces that tangent t turns into sine over cosine, and I know my algebra, I'm not going to be able to get to secant t, right? I'm not going to put that puzzle together. So that's why I want you to have that formula sheet in front of you so that you know what the pieces look like so that you can fit them together, right? Okay? Because putting a puzzle together without knowing what the pieces look like and what the pieces do with one another is very, very difficult, and you'll get very, very frustrated, okay? A byproduct, if you never use this stuff ever again, if you never go on to calculus, okay, and you never go into another field in which you need this stuff, a byproduct of it is that you will become very proficient at your algebra skills. Common denominators, adding fractions, fractions divided by fractions within other fractions within other fractions. There's a lot of practice of complex algebraic processes that we will have to get better at so that we can arrive at correct answers, okay? And I'll show you the use of, I think when I was in school, I sucked at these, to be honest with you. When I was your age, really, really bad at them, until I learned how I can manipulate my calculator to help me learn algebraic processes and to remember them and to check to see if they work, okay? So I'll try to do that with you as well. So we'll start up with that question tomorrow. No new homework.